Good afternoon. I'm going to report on the project on cognitive networks. The PI here is Professor Tara Javidi, along with a collection of co-PI and students that are presenting the posters outside. So the idea here is to use cognition to optimize at the network level rather than at the radio level. We have heard about cognitive radios quite a bit to optimize spectrum access. Here what we want to do is to exploit cognition at the physical layer to optimize at the network layer and suggest some improved designs, as well as gain some understanding on fundamental limits. The first research thrust that I'm going to present is the work of Professor Bhaskar Rao along with his student Yichao Wang. The idea here is that we want to exploit channel statistics in interference networks in the following sense. The realization is that collection of CSI, channel state information, is virtually impossible in massively large wireless networks, just because of the amount of data that you are required to feed back to have an estimate of all the channels of the network at each node. Therefore, a good fallback strategy is to gain only what it's called channel distribution information. Namely, you feed back from the users, not the whole state of the channel, but only the correlation metrics and the path loss information. And this can be done on a time scale of the order of tens of seconds rather than a time scale of the order of milliseconds. The particular scenario that was considered was in interference networks in which you have k pairs of nodes that wish to communicate between each other. And this is a MISO system in which each transmitter has multiple antennas and each receiver has a single receiving antenna. The communication channel is written as follows. You have that the output is given by the vector of the transmitting antennas, that's the desired signal, plus all the interference of all the other nodes, plus Gaussian noise. And the idea is that you're able to use information path loss and correlation metrics of the channel H to optimize for outage. So here this leads naturally to an outage framework where you want to optimize for outage. So we are not looking at coding over long blocks of time, but just one single shot where the packet can be lost. The channel is a correlated relic fadic channel. And the optimization problem is written as follows. You want to minimize the maximum probability of outage event subject to the power constraint. So P is the vector of powers that you want to get, and U is the beam-forming vectors that you want to obtain. This problem as written here jointly in the power and the beam-forming vectors is non-convex, and therefore has been subdivided into two steps. In the first step, it is assumed that you have fixed beam-forming vectors and you optimize only for the power. In that case, they came up, Bhaskar and his student came up with a fast algorithm that can optimize the power with the geometrically fast convergence rate. Of course, this is not optimal because you would like to optimize jointly. Optimizing jointly, they proved that is an NP-hard problem. However, they did propose an approximate algorithm that is also fastly converging, and the quality of the approximation depends on the structure of the correlation matrix that you have. And again, you are welcome to look at the paper and talk to Yichao that is around to get the details. Second thrust that I'm going to present is the work performed by the group of Professor Ramesh Rao. And the scenario here is to get one step more and go from optimization at the physical level to optimization at the network level. So here what we want to discover is in a scenario where you have two networks, and the colors didn't come out quite right here, but there is a red network and a blue network, and you want to decide what is the best policy to share nodes that can be used to route packets. Okay, so you have the option of sharing one node, two nodes, or multiple nodes, and you want to decide how and which nodes to share to optimize for certain performance parameters, such as the delay, for example. They set up the following problem. They considered a Bayesian learning framework in which offline you generate different scenarios, in which different networks with different nodes are shared. So you do this offline, you construct all these networks, and from all these networks you measure the topological parameters, so the topology may be the vector of flows, and the performance parameters that are the probability of having a dropped link or the delay or something like that, and you measure that and you come up with a Bayesian network that is able to predict, given the network topology parameters, the performance parameters. Okay, once you have that information that you have acquired, then you look at your actual network, and you do this in a second step, and you observe only the topological parameters. You feed that in your Bayesian network, and you infer the expected performance parameter. Based on these performance parameters, you can decide how to optimize based on an algorithm and your chosen performance metric. So here's a sample result, and more of this is in the paper, for the delay between nodes I and j. You see that as you increase the load on the network, if you were to share all nodes, you were in this situation. You share all nodes is optimal from the global perspective, but the two providers might not be willing to do that. They might want to share only a subset of the nodes. And with this framework, you see that by sharing only 2 nodes, you come pretty close to the optimum. The third thrust that I'm going to present is the work of Professor Tara Javidi and her student Mohamed Nageshwar. And here is taking again one step further and go to exploiting cognition to optimize the actions in the network in a dynamic way rather than in a static way. So we want to do the optimization online dynamically. The problem considering is that of dynamic schedule your packets depending on the change detection that you see in the network as time goes by. Let me give you a simple pictorial representation. In a network, when things change and the nodes transmit, the channel utilization changes. You want to sense these changes and act on your schedule depending on what you sense. Okay? Now, the problem of data collection and sampling poses a number of issues. Because sampling may carry some expense, sampling might be expensive, and also samples can be noisy. So you want to control for both the amount of resources that you're going to expend and the reliability of the measurement. And they call this active sampling. So basically you want to decide where to sample, which channels to sample. You have a certain number of channels and you have many possibilities on where to sample, to sense the channel, sorry. And you want to control the reliability of your sensing action. Let me give you a specific result. Suppose that you have a network with n channels, and if you were to know exactly the state of the channels, you would just pick the channel to transmit on where you know that your packet will go through. However, suppose that you do not have ability to sense all these channels, but you can only select one channel, transmit, and decide whether that channel was open or closed depending on the outcome. Then what you can do is to construct a Markov model of your channel such that you have an idea what is the most likely channel on which you can send your packet. And there is a trade-off between sending on the channel that is the most likely to get success versus sending to a channel that has less of a probability of a success, but is a channel that has not been explored very often, and therefore can improve your Markov model of the probabilities of success. So there is a trade-off between enlarging the space of view of your Markov model and the probability of success. And you can cast this in a framework of a classic restless bandit problem, which is a problem that is general NP hard. However, what they did is to find conditions for which a linear algorithm exists. And these conditions depend on the structure of the Markov model. And these are the papers where you can get some of these details. In another case that they considered is the case where you have multiple frequency channels. And in the previous example, there were no noise associated to the reading, while here you can sense the channel, and the channel can be detected as idle before sending with some probability, or it can be detected as busy before sending with some probability. Or you could sense multiple channels, and again, idle, any subchannel with some probability, or busy with some probability. Now, if you sense multiple channel, your accurate of your estimate is larger, the variance here is larger than here. So you can either concentrate on sensing a few channels with a more precise outcome, or you would like to sense a larger number of channels with a larger variance on the outcome. And this can be cast in the framework of an hypothesis testing problem, which they studied in these papers. As a final thrust, I would like to present some of my own work that is done in my group. And here we concentrate on the other part of the research, that is giving fundamental limits of what you can achieve rather than constructive strategies. One example is wireless networks, and this really ties in with what Professor Shlomo Shammai was saying today, that how can we operate a wireless multi-hop network? One way to operate it is to operate it multi-hop, just like we operate wired network. And what he was saying this morning is that we should not really do that, because we can do much better than simple multi-hops, because links in wireless are not really there. In case we operate as just a multi-hop, this is the performance we achieve. We learned that back in 2000, and we learned that compared to a simple TDMA strategy, where the channel capacity, aggregate capacity is 1, and 1 transmits at every time slot, so the capacity per user is 1 over n. If we operate in multi-hop, the capacity grows, but grows only as a square root of n, and therefore the per user capacity goes down as 1 over square root of n. So there is an improvement, but not much. And this was the point of Professor Shammai this morning, that was saying multi-hop may not be the way to go, because in wireless we have many more possibilities of cooperation, and potentially we can do much better than this. Some strategies have been proposed of cooperation, and they are based on ideas from distributed MIMO systems, so have a cooperation between nodes such that all nodes as an aggregate function as a MIMO, or based upon recent ideas on interference alignment. These strategies are based on exploiting the diversity that the physical propagation channel gives you. Since the channel is diverse, these guys can cooperate and have a much better throughput than the one presented before in the multi-hop case. In that case, the capacity would scale much better. Rather than square root of n, would scale as n. Therefore, if you have n nodes, each node can transmit at constant bitrate, okay, with these new techniques that were recently developed. However, these techniques are indeed limited by the richness that you have in your channel. So provided that your channel is sufficiently rich, then you can scale the system. And the question that we address in my group is exactly this. Can we learn how rich the channel is? How can we decide whether we have this diversity that we can exploit to construct our protocols? Since channel diversity is key, then we want to quantify and learn that amount of diversity. And the way we do it is to place this problem in the framework of electromagnetics. So really it's a blend of information theory and electromagnetics. And we try to characterize the diversity available in the channel based on different cut sets measures that we define. And for details, you can look at these papers where we define the notion of an integral that you can actually compute and get an upper bound on the amount of diversity that you have in your channel. And with that, I conclude the report. Thank you.
The last project that we're going to discuss is the